So let's say you're looking at the miles. So a regression is to predict values. So let's say you're in New York, you're catching a cab, and you know that you're gonna go 15 miles. You want to figure out how much is it gonna cost. You know there's a flat fee. Even if you drive 0 miles, there's a $3.50 flat fee just for getting into the taxi, right? And then you know for each mile I have to pay $2, right? So if you looked at a regression formula, you could say, okay, the predicted value y hat equals a, the intercept is the flat fee, so $3.50 for getting into the taxi, plus a beta, a slope, a price per mile. So x is our x values, so the number of miles driven, and the beta is the cost per mile. So if it's $2 per mile, we would say, we could plug it in, we could say we need to drive 15 miles, so the x is 15 times 2 is 30 plus the flat fee, 350. And that's what we have here. 3,350 is our total. Now, how did I know it was $2? I just had figured it out, right? Because 0 miles was 350, 1 mile was 550, the difference was $2. So I knew if you go 1 mile further, you go up $2 in the price. That's what our beta is. Now, we're going to take an approach where we use this formula here to calculate the slope, which the beta equals the correlation Rxy, so the correlation between x and y, times the standard deviation of y divided by the standard deviation of x. In this example, it equals 2. So how did I get the correlation? I said use this Excel formula, correlation between y and x, and then standard deviation, I used the Excel formula, standard deviation for y, standard deviation for x, right? And then I created a formula here that combines the correlation times the standard deviation y divided by standard deviation x. So that's how I got the beta. Now we have a formula to calculate the intercept, the a, which is a equals the mean of y minus beta times the mean of x. So here I did the same thing, figure out the mean of y, get the average of y values, and figure out the average of x. All right, and then we plug that into our formula to get the intercept. It is mean y minus beta times the mean of x. So now you have a, your slope, and b, your intercept, and b, your slope. So we can plug that into the formula, and if we wanted to predict values, we would use y hat equals 3.5, the intercept, plus 2 times x, 2 being the slope. This is what you can do, and then if we predict the cost, right, we plug in this formula, we can predict the cost, and then we can calculate the difference between our actual cost and what we predicted. You notice that the difference between what we predicted and what we actually had to pay is 0, because the relationship is linear. That is perfect. It's a perfect correlation of 1. So we know exactly what to expect, right? It would be unfortunate if you had to kind of guess every time you took a taxi how much it's going to cost exactly. It would be a little bit random, right? Sometimes you drive 15 miles, sometimes it's 3,350, sometimes it's 40, sometimes it might be 20. So if you have a perfect relationship, you can perfectly predict how much it's going to cost. So here we have this graph, and you see all the dots, all the data points are exactly on this regression line. And you also can see the r squared equals 1, so we explain 100% of the variation of this variable. You can also see here Excel calculated the regression formula for us. It flipped it around. It talks about the slope first, 2x plus then the intercept, 3.5. So now let's go a step further. Let's say that we don't have a perfect relationship, right? So what I did here for these values, I took the same formula that we used, $3.50 plus 2 times the value of x, the value of miles driven, plus a random number between 0 and 7. So that to add a little bit of wiggle room, right? It wasn't a perfect relationship, right? So that's why now when you see here, for example, 10 miles driven, it costs $29.50, right? Before, 10 miles driven cost $23.50, as an example. So now we do the same thing. We're going to first calculate the slope of b. So we took the correlation. We did the correlation between the y values and the x values, and you see it's still very high correlation, right? 0.98. Then we calculate standard deviation of y and the standard deviation of x. Note, standard deviation of x is the same because we didn't change any of these values, right? We're still interested in how much does it cost if you drive 0 up to 10 miles. But now to get the beta, we had to plug in these numbers here. The correlation times standard deviation of y divided by standard deviation of x. We use the beta here and now the mean values to figure out our intercept, our a. And then we can plug the beta and the a into our regression formula. We get 4.32 plus 2.51 times x. And if we look at what Excel came up with, Excel came up with the same formula, right? Just they flipped it around. And now the r squared, the explained variation, is 0.96, right? Which is actually 0.98 squared. Right? The coefficient of determination is the same thing as for the correlation when you have one predictor in the regression. Note that our prediction line is still linear, straight, but now we have sometimes we're a little bit below what we predict. Sometimes the actual values are a little bit above the curve, right? But we're kind of hugging this curve, going a little bit above, a little bit below. Now what's important here, the errors, the difference, or sometimes they're called residuals, right? They're not really mistakes, but they're the difference between our predicted value here, the box, and that regression line. So when we look at 4 miles, the actual data is here. So it's 16.5, but we predicted to be below. Right? We predicted 14.36, so we have a positive difference here. So the residual is 2.14. At mile 7, right, we found a value of 19.5, but we predicted that would cost 21.89 cents, so we were a little bit overestimating the actual cost. Right. So here it's the same principle as what we used for calculating the standard deviation, right? We take the differences, then we square those differences, we add them all up, and that will give us the sum of the squared errors. Then if you want to have the standard deviation of the error, we can take the sum of the squared errors divided by n minus 2, and then we take the square root of this. So here the standard error of the standard deviation of the error is 1.83. Now let's move on. So we see here very small error and the correlation is high. Now, well, let's say we have a medium correlation between x and y. Right? We figure out the correlation. In this case, it's 0.55. Right? So whatever we use as x, these miles driven are not as tightly related to the observed cost for the taxi. If we look at our beta, we figure out that now if you drive a mile more, you have to pay $1.40 per mile. And the intercept now is at $14, right? So what you can see is we already start out quite high, but then our curve is much flatter than before. Right? If we go look up here, you go up one unit on the x-axis, you go up 2 on the y. Here you go unit up on the x-axis, you go up 250 on the y, and then after this one here, you go up 1 unit on the x-axis, you go up 140 on the y-axis. And you can see our precision here starts to deteriorate slowly, right? Let's go again to let's say mile 9 here. The actual cost 9 was $37.50, right? But we predicted it to be $26.65, right? So we actually have a $10.85 higher cost than we predicted. Now we do the same thing. We add up, we square all these differences here. We add them all up, and we get the sum of the errors squared. Then we figure out the standard deviation. We see that now it's 7.39. So our estimate has a much larger standard error. We could also see that if we square the correlation of 0.55, it would be 0.31. We get a much lower explained variation, right? So because the relationship between miles driven and the cost of the taxi ride is not as tight, right? The correlation is lower, it's a less well-suited predictor for predicting the cost, right? Now, here somehow other factors influence the cost of the taxi drive rather than the miles driven. If we take this even further and we take a smaller correlation, here a correlation of 0.22, right? I introduced a bigger error. Now you can see the regression line is almost flat, right? The error becomes really large. We start out already at over $30. Our intercept A is now $33. And if you look at the miles driven, right, over average here is 1 mile driven, $1.04 more in cost. Right? And if you look at 4 miles driven, the actual cost here was $62.50, right? And we predicted that it would be $37.30. Now again, right, you drive 1 mile more. Here in this example, you actually had to pay less, right? For 5 miles, you only have to pay $45.50. So you can see how now the relationship between driving miles, distance, and the cost is very low. And consequently, the sum of the square errors go up and the standard deviation becomes much larger as well. So this here an example of how the correlation between the x and y variable affects the quality of your prediction, right? How much you can predict depends on how much are these two variables related to each other. And this then is reflected in your slope and in the tightness of the data points around that linear curve.